Hello, welcome, and thank you for choosing to learn with Materialise. My name is Toon Roels. I am Director Process Engineering and Quality at our manufacturing division here at Materialise, and I have worked in 3D printing since 2006. Today, I will give you a quick introduction to our materials and technologies. In this session, I'll cover a few basic topics that will give you a solid understanding of your 3D printing options. Firstly, we look at why you should consider 3D printing, what makes it unique, and the advantages it has over traditional manufacturing techniques. You'll also get a quick look at the different 3D printing technologies, from selective laser sintering to multi-jet fusion and many others. I'll explain you how each option works and when it is the right choice for your project. And lastly, we'll briefly explore the different materials you can choose from and their characteristics, both metals and polymers, all with different strengths and benefits. Let's get started. In this session, we will talk about additive manufacturing, polymer technologies and materials. And I will talk you through the various technologies and materials that do exist and offer you a framework to make your judgment and choice on which polymer technology and material is the right one for your application. But before we do that, let's take one step back and let's look at what does determine the performance of a manufactured part. Let's think of conventional technologies and let's take, for example, this garden chair. So my statement is that there are three components: design, material, and process that make up the performance of this chair. Somewhere a designer has chosen 4 legs for this chair, has given it a certain wall thickness, has given it a certain back length, etc. And by doing so, he has put a tremendous stamp on the performance of this chair. And also, there is somewhere a material engineer who has selected one polypropylene grade from the many because he thought that was the most suitable polypropylene grade for this outdoor object. And by doing so, he has also put his stamp on the performance of this plastic chair. And yes, this chair has also been injection molded, and by fine-tuning the injection molding parameters, the professionalism and the quality of the injection molder has also contributed to the quality of this chair. And now, I know it's a bit arbitrarily, if we try to judge the quantitative contribution of these 3 factors, I would say that design and material do contribute to a large extent to the performance of this chair. And yes, if you then look at what the injection molder and what can go wrong in the injection molding process have contributed, I feel that's probably a minor factor. Let's call that 10%. And these 3 make up the performance of the chair. If we now look, on the other hand, how that sits with additive manufacturing, you would end up with a more complex chair, and also these 3 factors would contribute to this chair. But as we praise 3D printing for the design freedom, I hope that you would agree that potentially the designer has a bigger stake in the performance of this chair than all of the other components. You use 3D printing for the freedom of design, and the designer can really go wild and put his stamp on the performance of this chair. And as I only have 100% to divide, I say that I attribute 20% to the process and 20% to the material. If we look at 3D printing processes, 3D printing is a young technology, a lot can go wrong. You build layer by layer, vector by vector. So a small variation in the process, and the process is also not that mature as an injection molding process, makes up that the process is proportionally more important than with injection molding. And to add up to 100, I say 20% of the performance is determined by the material. So why is this so important? So I think that everybody who wants to make use of 3D printing should realize that design is the dominant factor. And you typically see also that a 3D printing company, they have more design engineers than in classical conventional technologies. So design is very important, but in order to successfully design with 3D printing, everybody needs to understand the contribution of the process and the material. And in the rest of the presentation, I will only talk about the process and the material. And that's basically what everybody who works with 3D printing should understand what is the contribution of process and material, in order then, in the next step, to successfully design and build a business out of 3D printing. And so basically, what do you need to know when it comes to the process and the material to call yourself familiarized with 3D printing? Calling yourself familiarized with 3D printing is not an easy thing nowadays. If you look at the world and the wide choice of technologies that do exist, you rapidly come up to more than 20 different technologies, plastic, polymer, additive manufacturing technologies, and they all call themselves 3D printing. Imagine that you're not familiar with 3D printing and you walk into a TCT fair or in Formnext fair, you would see all of these technologies around you and you would be very puzzled and you would feel not so much at ease and not know which technology and which material is now the best for your application. If we say 20 technologies, imagine that they all come with 10 materials. That means that there is a potential of more than 200 materials that you should choose from as well. So you will agree that at first sight, the landscape of 3D printing technologies and materials is very, very complex, and it's not easy to find your way in that. In this landscape, I will give you some guidance on how to read that landscape and find your way into it. It all comes much easier if we divide these 20 technologies or these 20 plus technologies in 4 categories. And basically, you should ask yourself 2 questions. The first question is, if I look at a technology, does it work with a liquid as a raw material, or does it work with a solid as a raw material? And by categorizing these 20 plus technologies into the 2 categories, you will immediately split this landscape in 2. Some technologies work with liquids as a raw material, and by default, by principle, we talk about the reactive technologies where chemistry plays a lot of a very important role. You start with a liquid raw material and you need the polymerization to take place while you 3D print. So these are very complex technologies. And basically, you look at a chemical reactor that at the same time gives shape to the plastic object. You should also realize that all of the materials that are being used in liquid 3D printing technologies are being invented for that technology. These materials did not exist before 1980. So it's very complex chemistry made to fit the 3D printer. We talk about young materials, young technologies, and that also has an influence on the actual performance. And in the end, you get a plastic, and in this category, we talk about a cross-linked polymer. On the other hand, if we look at the other technologies, so some of these 20 plus technologies do start with a solid as a raw material. Those technologies, they make use of existing thermoplastic materials. So in this category, we have no materials that have been invented for 3D printing. No, we make use of materials that do exist for extrusion and injection molding. And at the best, they have been modified a bit to fit the 3D printing technology. Modified mainly when it comes to shape, like a pellet or a filament or some powder. But in essence, we can, the pool of materials that you select upon is a very performant existing class of materials that everybody understands. So even if you're not familiar with 3D printing, the material used in this category will sound you very, very familiar. So, and if we divide the 20 plus technologies in these 4 quadrants, it would look like you see on the slide. And no surprise, what you then see as the key example of each technology in each quadrant, you would see the 4 oldest versions of 3D printing technology, polymers, like bed-based liquid technology. The key example of that technology would be stereolithography. That was the first invented 3D printing technology. Then the second invented 3D printing technology was laser sintering. That is the key example or the archetype, if you want, of the bed-based solid technologies. Later on, fused deposition modeling was invented. That is the archetype of the solid selective deposition technologies. And a couple of years later, in the 90s, jetting liquid droplets was added. And this is then the key example of selective deposition and liquid technologies. And you can basically say that of the 20 plus polymer additive manufacturing technologies that we have today, they all are derived from one of these four technologies. And they can also not hide that they are being derived of this key technology because they still carry the main characteristics that are related to the position in this quadrant. And yes, some of these 16 technologies that have been invented after these four ones don't let themselves squeeze exactly in one quadrant. For example, if you look at multi-jet fusion technology, you can say that it's probably 80% of a bed-based solid technology and a small character, let's say 20% of jetting on top of it. But again, if you understand that multi-jet fusion is 80% bed-based solid and 20% selective deposition liquid, that will help you tremendously in understand what you can do and cannot do with the multi-jet fusion technology. So this makes life much easier. So my call is try to understand in which quadrant the technology sits that you look at, and you will automatically understand a lot of what the technology is capable of and what it is not capable of. And it's by putting these 20 technologies in this quadrant that you can understand how you can use this technology. At first, there is the material choice. Like when you are in a quadrant and when you look at a certain 3D print technology, it automatically comes with a portfolio of materials. So by selecting a technology, you limit the choice of materials that you can have within that technology. For example, it doesn't make sense to say, well, look, I would like to have ABS and I want it to be printed by stereolithography. That doesn't work. You choose a technology and automatically you have access to certain materials. And these materials, they do have an inherent performance, and I depict that in the shape of a polymer performance pyramid. And you do have materials that score high in thermal resistance, chemical resistance, brittleness, fire resistance, and you have materials that inherently have a lower performance. So this is the inherent performance pyramid of the materials. And then if you look at the process-induced factors, like if you have chosen a certain material and then it comes with a certain technology, the technology also puts a stamp on the performance of that material. And then I talk about effects like porosity and anisotropy. Anisotropy, in 3D printing, you do build layers on top of each other and you don't have homogeneous properties in Z direction versus XY. And the extent that some technologies do suffer from this anisotropy or not is heavily determined by the position in the quadrant. And the same with porosity. If you choose a technology that sits in a certain quadrant, automatically you have a certain porosity. And again, some quadrants come with high porosity and some quadrants come with low porosity. So these are the process-induced factors that have an effect on how much of the inherent material performance you in the end might enjoy or not enjoy. And again, other factors that are more design related are also determined by the position in the quadrant. Let's, for example, look at whether you can design multicolor parts and print multicolor parts or print in multi-materials, even digital materials or gradient materials. That is not so much determined by the material, but again, more determined by the actual position in the quadrant. Some technologies or some quadrants come more easily with multicolor options than other quadrants. And another very important factor, especially again when it comes to the design and the freedom of the design that you might enjoy, is whether you need support or not. Certain positions in the quadrant make that always you need to rely on support, while other quadrants, they don't need support generating structures. And that again means that you can enjoy more of the design freedom. And if you then put all of these factors, the materials you have and their inherent performance, whether this material performance is affected by porosity and anisotropy, and whether these technologies can be used to print in multicolor or not, and whether you enjoy the full design freedom or not, that ends up then in how suitable is this technology for series manufacturing. And in the end, it's all about like how can I now select a proper 3D printing technology and a proper material to serve my application? So it's very often, let's say, the suitability for series manufacturing that makes people to choose or not to choose for a certain technology. And when it comes to positioning these 20 plus, or if you want, these 4 quadrants in a simplified scheme, I would like to position them here in this axis system, where I do display on the x-axis the visual quality. Visual quality, that means things like surface quality, porosity, ability to print in color or not. You will see that the 2 quadrants represented by stereolithography and polyjet do score relatively high on the visual quality. I position polyjet a bit higher than stereolithography because you can reach lower layer thicknesses that come with more perfect surfaces, and also because with polyjetting you can print in multi-material and even gradient materials. So those 2 technologies, they score high on the visual quality side, while I do not position them so high on the material functionality axis, because these technologies and the materials that they have in their portfolio, they do not particularly excel in durability or thermal resistance or chemical resistance. So these technologies come with rather less functional materials. And of course, if your application is situated in somewhere the area where you need high visual quality and you don't need such an excellent raw materials or materials, then probably SLA or polyjet or your technology of choice. But if your application is very demanding when it comes to material functionality, then the likelihood is higher that you will turn to fused deposition modeling or laser sintering, because these technologies, they have access and they come with very performant materials. I do position here laser sintering a bit higher than fused deposition modeling because, in my feeling, the fact that in laser sintering you don't have such a pronounced anisotropy, and it also comes with a porosity that is a bit lower than an FDM, I feel with laser sintering you manage to get out more of the inherent performance with the laser sintering technology than with FDM technology. And of course, also we realize that many applications, they do require high functional and good visuals. And today, and especially if you look at the 4 archetypes of 3D printing, you need to do extra, you have to undertake extra steps in order to reach that upper right corner. If you start from the solid technologies that don't come with such a high visual quality, you will have to spend a lot of time and effort to post-pros and try to improve the surface quality. If you want to reach the upper right corner coming from the SLA and polyjet technologies, you might be even needed to make a step to another material and use the SLA or polyjet parts as a master, or for example, you will have to make them stronger by putting an additional coating of metal plating on top of it. So that's a hard way to crank up the performance. And if you look now back to the 4 archetypes and how that has evolved from 4 3D printing technologies to 20, you will understand that these 16 other technologies also somewhere occupy a space in this graph and might be more or less suited to serve your application. Just as an example, look at multi-jet fusion. Multi-jet fusion is again a better version of laser sintering when it comes to visual quality. You do print in lower layer thickness. You have also less porosity. And due to the fact that you have higher densities and less porosity, you do proportionally extract more out of the inherent performance of the materials that you use. So multi-jet fusion is a bit an improved version of laser sintering, and therefore it might be easier to serve your application. You will proportionally need less post-processing when you start with multi-jet fusion than laser sintering. Another example that I would like to position in this graph is, for example, the clip technology invented by the company Carbon, where they really made a step change improvement in the performance of the liquid technologies, and you come closer to the high functional versus good visual desire that many applications have. And it is basically by looking at the 3D printing landscape and understanding the origin and the history of the 3D printing technologies and to which quadrant they are linked most, that you can select them on the suitability for your application. So I hope that by providing this framework of the quadrant, I give you somewhere a guidance in selecting better which technology is best suited to serve your application. So, and if you don't find your way in the landscape, don't panic. You can always turn to companies that have a lot of expertise in 3D printing, like Materialise, and starting from the application and your needs of your application, we will together with you try to select the best material and the best technology for your application. And from there, you can then take it and we will be able to get the best out of 3D printing. Thank you for joining this tutorial, and don't hesitate to reach out to our experts at the contact address that you will find at the end of this video. So, there you have it. A first look at your 3D printing options. In those videos, we'll take a deep dive into each option with expert advice on when, where, and how to use them. In the meantime, you can also explore more content like this via the links below. And if you have any questions about our courses, our services, or anything else related to 3D printing, you can get in touch with our team at the address you see on screen. Thank you again for learning with Materialise. We'll see you next time.